Hello, everyone. Welcome to the latest edition of Coffee and Capture, where we have conversations on intelligent document processing. Thank you for joining today. Hopefully, you've got your coffee or some other kind of caffeinated beverage in front of you. I have a French press. I just love French press coffee, it makes it nice and strong. Today is going to be a little bit different because we've got a deeper type of topic. It's called The Secret Life of the Confidence Score. And the reality is that confidence scores can be a really deep swamp in terms of just the concepts behind it and how they should be used. So I'm going to attempt to try to convey to you in as short an amount of time as possible the understanding behind what a confidence score is so that you can use them better. Now, we have a number of materials or educational materials, including an ebook that you can download and read that I've actually taken some of the material out of it. It's a really good educational type of ebook around what confidence scores are. It is available on our website, and it's titled Data Science and Intelligent Capture. So I highly encourage you to go and get that. So first, let's talk about confidence scores, and you'll notice maybe that I've rearranged the titles. It's the why before the what. Typically, it's what and then why. But I think it's really important on why you would understand why you would need to use confidence scores, why they're important. Otherwise, you're not really going to be interested in the what they are. So confidence scores really are the key behind enabling real or high levels of automation. So typically in automation, what most organizations expect is that they have stuff that doesn't require tasks or whatever that don't require any kind of human intervention, right? So automation in terms of autonomous driving vehicles is you don't want to have a driver sit and babysit the computer and turn the car or whatever. You want everything to be taken care of all by itself. And confidence scores for intelligent document processor are the real key there. Without confidence scores, you can automate tasks, but you can't rely on those tasks being accurate so that you have to verify pretty much everything. And the picture that I increasingly use is this one. So if you look from left to right, left being the far left being a 100% manual process, the middle is where most organizations are. So they've implemented some sort of intelligent document processing, and they're achieving an appreciable level of automation in terms of automated data entry or automated document class assignments and things like that. But they're not able to, so they can reduce staff or reduce staff workload, but they're not able to, if they're not using confidence scores, to completely automate stuff. So what you have is most of these guys here or gals are actually here because they need to verify or review 100% of the output to ensure that it's accurate. But when we introduce confidence scores as a way to control what needs to be reviewed and what doesn't, we can further significantly boost automation. So now we only have to make use of the equivalent of two staff to review what's left, what to review what genuinely is more likely inaccurate data so they can make corrections and things like that. So you can see here we're going from quite a significant workload to really just insignificant. And the key here is use of confidence scores. So most organizations, unfortunately, don't use confidence scores to their greatest extent. And how do I know that? Why do I know that? The answer is that in most cases, when we talk with prospective clients, there is this presumption that confidence scores equal probability, and that is just not the case. In a way, they're related to probability, but they in themselves do not represent probability of any type of automated task being accurate or not accurate. For example, a score of 80 does not equate to an 80% probability of that automated task being correct. It just doesn't. There are a number of reasons why we're going to dig into that. So unfortunately, most organizations are utilizing them in a probabilistic way, not knowing that they don't have a direct relationship directly. And so they're setting confidence scores or their thresholds to something like 95 or greater, believing that what that's really doing is it's setting the system to only output data that is 95% has a 95% probability of being accurate, or even higher. Let's say they set it to 99, and what they're ultimately doing is they're forcing a review of close to 100% of that data. So that is the thing here, and you don't want that. So what is a confidence score? How do we even get confidence scores? So a confidence score essentially is just a number assigned to a task, but it's not just a number. There's a way that we get the number from the system. They typically range between 0, always 0, but they might go to 100, they might go beyond 100. There's some systems that have maximum confidence scores of 1,500, which definitely means that it's not a probabilistic type of number. So examples here, this is kind of pseudo XML. This is in a loan file automation task. We might have to do some document classification, always typically. And this is a title insurance, and we've got a score here. So we've got the document class equals title insurance, and we have a corresponding score of 87. In the case of data entry, automated data entry, we have an insurance amount. We have the value here equals, and then we have a corresponding confidence score of 78. In neither of these cases is the score itself probability. So it is not an 87% probability that this class is correct, and neither for the 78. So how do we get these scores? What do they mean? Ultimately, confidence scores come from the software that outputs them. And we start with training. Data scientists train machine learning algorithms, most likely neural networks, and even more likely deep learning neural networks of some sort of variety, on specific tasks. Now, these specific tasks could be just things like OCR. So convert characters and words within an image to text that is machine readable. So that's an example. It could be something more specialized, like training machine learning algorithms to understand the difference between one document within a loan file versus another document in a loan file. So very, very specific types of stuff. But in either case or any case, you're training the software on a large amount of this data. The sample size has to be significant. Most often it's 100,000, or greater. So these data scientists will then analyze the output of these machine learning algorithms, and they'll make adjustments. They might make adjustments to the input data to emphasize certain types of use cases over others, but they'll also adjust the algorithms. They'll make adjustments to how things are weighted with an objective on improving both the performance in terms of accuracy. So, let's say the system has a bunch of output, and it starts out with 80% of that data output being correct. Their goal is ultimately to get 100% of that being correct, but that's impractical. I mean, systems aren't perfect just like humans are. But their objective is to optimize the overall accuracy of that output data. But they're also, if they're doing it right, they're also trying to optimize the reliability of the associated confidence scores, those numbers that go with each type of automated task. So ultimately, the objective is to create a high level of correlation. What does that mean? It means that we want confidence scores to be higher when the data is accurate, and we want confidence scores to be lower when the data is not accurate. So they're looking at both these things. So is the data accurate, and what's the corresponding confidence score? If the data is accurate and we've got a score of like 5, then that's a problem, especially if it outputs a lot of accurate data with a lot of low scores. So they'll make adjustments and do that. A lot of this stuff is happening behind the scenes. So confidence scores, ultimately, you might ask, after the data scientists go to a lot of trouble to create a high-level correlation, why can't that correlation be probabilistic? In the truth, in some cases, it can be. I mean, if you're using OCR that has been trained on a specific language like English, and they've got published accuracy rates, then there's a high chance that an output of a letter with 99 as a confidence score, that can be treated close to 99% probability that it is correct. But where we start to deviate from that is when you introduce more complex use cases where there's no practical way data scientists were able to train the software to tackle. Let's use that loan file document classification task as an example. There is software out there, including ours, that is pre-trained on this stuff, and we can make sure that confidence scores are more reliable in there. But there are just a whole range of use cases for which there's no practical way you can train stuff in the lab so that you're optimizing both for accuracy and reliability of confidence scores. The confidence score should still be reliable, but what it means is you're not going to have, data, optimized to such an extent or output that you've got 90, you've got this really big, nice correlation, a very strong correlation. So what do we do in that case? We have to create a sliding scale. If the confidence scores are still reliable, and they should be if the software is designed correctly, regardless of what use case we have, then it's up to us to analyze the data and then create our own scale. So this is an example of how we would do that using CMS 1500, otherwise known as HCFA claims. And we're looking specifically at the data element, patient date of birth. And you actually, if you're going to do this, you have to do this for every single type of task. So if the task is classifying documents, you've got to look at the output of the document classes that were assigned along with those scores. If we're doing data entry, we have to look at this as at a data by data field level because they're going to be different. So in this case, I'm looking at date of birth. I've got the output of the system. So this is the transcribed date along with its associated confidence score. And if the software is designed right, what you're going to see is if you sort them by confidence score from highest value to lowest value, what you're going to see is there's a correlation between correct output and higher confidence scores. So we can see here that when we look at correct stuff, when we sort it by confidence score, we could see that the number of correct data is also sorted mostly, right? That's what you want to see. So you can immediately visualize this and see whether or not the confidence scores are reliable. So it's next, presuming that we have a good reliable confidence score for a specific data value, we're going to then identify what is the specific confidence score, or if we're looking at larger data sets, what is the score of scores, few that represent this kind of breakpoint between incorrect values or output and correct output. And this is your confidence score threshold. Ultimately, what you want to do is you want to optimize this because this establishes the reliability, or this point of reliable data versus data that needs to be reviewed. And if you have enough of it, you can calculate the accuracy rate of this reliable data. So if we're counting these and we have one incorrect value here and we do this on a large set, we can get a statistically reliable accuracy rate for everything above this confidence threshold. That's ultimately what you want to do, and you have to do this on every single data field. But this is what you have to do. So why are scores not always, are scores reliable or are they not? I've said this before, so it should be implied that we don't always see scores that are reliable. The answers can be many. It may be that it just wasn't the focus of the data scientists that were developing the software, but it could also mean that the types of tasks are just outside the realm of what we consider for, what the software is programmed to do. But ultimately, how do you know if scores are not reliable? Well, just as we saw this area where we're sorting by confidence scores from highest value to lowest value, and we can start seeing that they're clustering on correct and incorrect, the opposite is true. So this is an example where we've sorted by confidence score value again, and what we see here is just a smattering of incorrect and correct answers. What that means is if I set any kind of threshold, it doesn't matter. I may get a high percentage of that output data being incorrect, which forces me to have to review every single data output from the system. And this is where most companies are. I mentioned that most companies are doing this just because they're not using confidence scores the correct way. But it also can be that if you take a lot of time, you still won't get to that reliable confidence score threshold just because the software can't achieve it. So ultimately, the upshots are if you're using scores out of the box, so to speak, thinking that they're probabilistic, you're not going to achieve any true automation. You're going to have to verify stuff. You've got to analyze the output and the scores in the way that I showed in the illustrations, based on your own use cases and your own data. And you have to identify the thresholds that make the most sense. So you have to understand what that sliding scale is at a data element by data element level or field level. And then realize that some systems, no matter how much you spend on this, can't achieve it. So it behooves you to do these tests very early on to see if this is even achievable with your software. Because if it's not, you're just wasting time. and you want to focus on getting software that can actually do it. So at this point, I think that's the end, and we'll be happy to take any kinds of questions.